the final three types of equations, chemical reactions we're going to talk about are acid-base reactions, gas-evolving reactions, and redox reactions. So this is 3 separate sections in the textbook. This one's going to be kind of a long video. All right, so let's begin with acids and bases. Quick recap, an acid is a substance that produces protons, H+ ions in water. To complicate things, as soon as we make them, they stick to a water, so it really would be represented as H3O+ hydronium ion, but don't worry about that. H+ in this case, for right now, is going to be fine. And then bases are ones that, when I put them in water, they produce hydroxide ion. So it's going to be mostly a salt that has a hydroxide anion. And another definition we'll talk about in the acid base is that it also is one that it accepts a proton, would be an alternative one. But we'll focus on the making hydroxide for strong bases in this class. Okay, so acid-base reaction. I take an acid, I take a base, and it's going to form a water and a salt. That's kind of my operational definition. When you react an acid and a base, it's going to make a water and a salt. What's happening, we also call these neutralization reactions, and what's happening is the acid forms H+ ions, the base forms hydroxide ions, and an H+ ion and a hydroxide ion can combine together, form a covalent bond, and make water. I'll still have 2 ions left that were originally the anion of the acid and the cation of the base, and they will form the salt. So that's what's happening. It really is a double replacement reaction. It's just that we first form the proton and the hydroxide, and then it makes a water. But we can treat that as a double replacement if we treat hydrogen as if it was a metal and it was already a +1 ion. Technically speaking, anyways. So the mechanism of an acid-base reaction is that I start with a strong acid or even a weak acid, and it's going to break up and form protons. So in this case, it dissociates, it ionizes, it forms protons, and the other ion left is nitrate ion. And then I have a base. It's going to dissociate and form a cation and then hydroxide ion. And now my proton and my hydroxide ion are going to form a covalent bond and form a water molecule. So I end up with water molecule. I have some remaining ions left, in this case a sodium ion and a nitrate ion, and they're going to form the salt. And I can write them, normally when we're writing them in a molecular form, I would write them together with subscripts that I need based off of what charges they are, just like we were doing for the other double replacement reactions. Okay, so let's look at an example. If I had H2SO4 and NaOH, H2SO4 is an acid. I know it's an acid because it starts with H. Also, I should know it's one of the strong acids. Sodium hydroxide, I see it's got a hydroxide as an anion. It's a base. So I can treat that as if I'm going to treat the acid as if the H+ was already an ion, as if it's an ionic compound. I swap the anions, and then I'm going to use the charges of the ions that I have, always H+, and then OH-, and then the other ions, I'll figure out the chemical formula of the salt based off of the ion charges. Since sodium is a +1 and sulfate is a -2, it'd be Na2SO4. And then I can realize that HOH is water. So I'll rewrite it as water. This is technically, it has basic properties. It could be considered a base. It would be a weak base. But I'm just showing you, I could also do it with an acid with something that maybe doesn't look like a base. And in this case, as I swap the sulfate and the oxygen, I still end up with water. It's just that it's water coming from H+, 2 H+, and the 2- oxygen. And then I end up with the same product of sodium sulfate. All right, so that was acid-base reactions. Gas evolution reactions, the operational definition is a reaction that makes a gas product. Done. So how do you get a gas product? We're not going to see it with precipitation reactions. We're not going to see it with acid-base reactions. It's often not even a double replacement reaction unless one of them was a sulfide. So a reaction between an acid and a sulfide could form, the acid has H+, the sulfide has S-2, forms H2S. I need you to memorize that if you make the product of H2S, H2S is a gas. So that one you just got to memorize. There are also 3 reactions we're going to talk about that make unstable products, and they can break down to form a gas. We're also going to see redox reactions that form gas state elements. Hydrogen, nitrogen, oxygen, chlorine are good examples, are also gas evolution reactions. You need to focus on, did we make a gas? And the only time I'm going to ask you to predict is if we're either it's making H2S or if it's making one of these 3 unstable products I'm about to show you. Everything else, I would tell you it's a gas state, and that's how you would know that there was a gas made. All right, so these 3 unstable products that if I form this salt, and they're all, ones that involve either an acid or base, if I form it, then it's not stable, it's going to break down and form water and some gas. So if you have a double replacement reaction between an acid, which would produce H+, and a carbonate, which would produce CO3 negative 2, and those combine and make H2CO3. H2CO3, also called carbonic acid, is not stable. It's going to break down to water and CO2. So when I see H2CO3, I want to replace it with water and CO2 gas. If I make an acid, H+ is coming from the acid, and a sulfite with SO3 2-, I would the H+ ions and the sulfite ions are going to form H2SO3. That is also unstable. It will not exist as H2CO3, as the H2SO3. It's going to break up into water and SO2 gas. And then if I'm reacting an ammonium ion with a base, the ammonium and the hydroxide, when I form NH4OH, not stable. It is immediately is going to break down to water and ammonia gas, NH3 gas. So if you need to recognize these 3 will break up and form these 3, and these are gases. You also need to recognize that if I form H2S, H2S is a gas. I don't have to break it up. It doesn't form anything else. It's not unstable, but it is a gas. So, and all of these note that these 2 would be to make them, I'm going to have to be reacting with an acid. NH4 could be reacted with something, although the OH- is coming from a base. So these are going to form when I have either an acid or a base in there generally. There are other ones that form gases. I won't expect you to predict those products though. So again, wrapping this up, we've seen a lot of double replacement. I just kind of remind yourself of a couple double replacement hints. You're going to find the 2 halves of each ionic compound on the reactant side. And you're going to write each half with their charge. Go ahead and get those charges on the right-hand side, and you're pairing them with the different anion. Use the charges to determine the subscript of the anions of the ionic compounds of the 2 products. And then to determine if there's a reaction, you have to like a solid, a liquid, or a gas. So now I'm going to be looking at what are the states of the products. I'm going to use solubility for any of the ionic compounds. I'm going to use solubility rules to determine if it's going to be solid or if it's going to be aqueous. This should not say I here, that should say S here. I don't know what's wrong with that one. If it's not, I want to see is one of the products hydrogen gas or oxygen gas or chlorine gas, but we won't see that show up when we're predicting. If you have H2CO3, H2SO3, and H4OH as a product, break it down further into water plus the remaining gas. If not, if you see one of the products is water, if I form water, it's a molecule, it will be liquid. It won't be aqueous, it's liquid. So acid base makes water, it's in liquid state. That's not aqueous, so that's intact, it would remain intact. That would make a liquid, so we're good. If I don't have at least one gas or solid or liquid, so both of my products are aqueous, then it would be considered no reaction, nothing really changed. And after I've done predicting the products and identifying the states, then I go about and I will balance it. Because it's a swapping of ions, if there are polyatomic ions, you can consider them as if they were an element. It makes it a little bit easier to balance. If you have water product on the product side, you can consider it as a combination of an H+ ion and an OH- and balance H+ and OH- ions on either side. Again, that just makes it a little easier to balance. The final type of reaction is redox reactions, and this is kind of like a whole new ball game. So we're not doing double replacement. This is instead about transfer of electrons. If one species is reduced, reduction is a gain of electrons, and another species is oxidized. Oxidation is a loss of electrons. So the oxidation is losing electrons, those electrons get gained by the thing that's being reduced, and I end up with a transfer of electrons, and we're going to call this a reduction oxidation reaction, but we simplify it and just say redox. So one reaction is oxidized by losing electrons. It transfers those electrons to the other, another species, which is going to gain them, that's going to be reduced. So they always happen in pairs. Electrons are not stable by their own, so when something loses, immediately something else is going to grab those electrons. So they'll always happen in a pair of each. So we're going to break up the reduction and oxidation into half reactions. Again, we'll never see just a reduction or just an oxidation. They're always going to happen together. But it's just easier to manage if we break them up into half reactions and look at what's seen with the oxidation and what's seen with the reduction. So in a reduction half reaction is gain of electrons. It'll be some probably positive charged ion is going to gain electrons and become neutral. In an oxidation half reaction, we have a neutral element breaking down, is going to lose electrons and become a cation. So with my metals, this would happen with my metals. It could also look like a negative ion gaining electron, and this could look like a negative electron losing its negative ion losing its electron and becoming neutral would also classify as an oxidation. We don't see that very often. The number of electrons depends on the change in oxidation number. Let's go back to those oxidation numbers. When the oxidation number of an ion decreases, it's being reduced. That's where the term reduction comes from, is that the oxidation number is reducing. So the charge is reducing from like a +2 to a 0. If the oxidation number increases, that's being oxidized. So when I'm going from 0 to plus, I'm increasing in oxidation number, and that would be losing electrons, so that's going to be an oxidation. So as I look at these, also, well, you're going to see, and I'm asking you on the homework about reducing and oxidizing agent. An agent is something that aids, so I can think of the reduced species as something that's aiding the oxidation. And I can think of the oxidizing species as something that's aiding the reduction. So I usually just cross out the word when I see the word agent, cross it out, and flip it to what is the opposite thing. The reducing agent is the thing that's being oxidized, and the oxidizing agent is the thing that's being reduced. And that makes it a little bit easier. All right, so let's go on and look at some examples. Reminding yourselves about this oxidation state, the proper way to do it is to draw the electron, the Lewis structures, and assign, for every bond, assign between two different elements, assign it to the higher electronegativity one, and determine the oxidation numbers. But a lot of times we just use algebra and figure them out. It's faster. So I do need to, if I'm going to do that, kind of remember to get the algebra, I'd have to know some of the ion's charges already, or oxidation states. So if I have an atom or an element in diatomic state, 0. If I have a monatomic atom, ion, so I have hydrogen ion, I have Na plus ion, that's going to be the charge, the charge is the oxidation number. So sodium +1 is +1. So all of my normal metal ions will have, their oxidation number will be their charge. If I have fluorine in a covalent compound, it's going to be -1. So in other words, let me back up. So what this is also saying is that when I have an ionic compound, there's going to be the charge, the oxidation state is the charge. If I have an ionic compound that has a polyatomic ion in it, I now have to, that's a covalent one, that's where I'm going to have to assign the different elements in there to different oxidation numbers. So fluorine in its compounds is going to be -1. Oxygen is almost always -2. I'm not going to give you tricky ones where it's -1. Hydrogen is almost always -1 in its covalent compounds. It's a very low electronegativity one, so almost always it's +1. So if we assume that oxygen is -2 and hydrogen is +1, and that works 99%, well, maybe 90%, 95% of the time. For the examples I'm going to give you, it will work. Then I know enough of the oxidation numbers to figure out the ones that I don't know using algebra. Okay, traditionally, balancing redox equations is a challenging task because now I need to make sure that the number of electrons that are lost in the oxidation is equal to the number of electrons that are gained in the reduction. but they're different species and they may not need the same number of electrons. So I have to balance all of the atoms as I normally do in balancing electrons, but I also have to make sure the number of electrons are balanced, which means I need to break it up into half reactions. So I can see what's happening, how many electrons are being involved in the reduction, how many electrons are being involved in the oxidation, and then scale them appropriately to make sure I have the same number of electrons. And again, also, once I have the same number of electrons being gained and lost, like they cancel out of the overall equation, so I can't see them. So we're going to break them up into half reactions, scale it, and then add them back together. So we're going to identify what is oxidized and what is reduced using their oxidation states. So I have to find the oxidation numbers of everything. And then once I have the oxidation numbers, I'm going to break up into an oxidation half reaction. I'm going to balance the oxidized species, then oxygen, then hydrogen, and then add electrons. And then I'm going to make the reduction half reaction. I'm going to balance the reduced species, then oxygen, then hydrogen, and then add the electrons. And then I'm going to scale the reactions, the two half reactions, and multiply them until, if they need to have the same numbers of electrons. And then I'm going to add them back together, and I'm going to cancel out the electrons. All right, in much more detailed steps, and again, this works better when you're working side by side with these steps in an actual problem. I'm going to determine the species being oxidized and the one being reduced by comparing oxidation numbers of every single element in every single compound from the reactant to the product side. And I'll see one is changing, one oxidation number is increasing, one is decreasing. That's how I identify my species. I will write and balance the half reactions. So I'm going to do this once for the oxidation and once for the reduction, but going in and sort of double checking. So we're going to write the reactant, an arrow, and the products. So we'll keep the same formulas as the original equation. So even though I've identified sulfur as the thing that is changing oxidation number, I'm going to write it in its full form of whatever the sulfur is in the reactant side and whatever it is in the product side is as it is in the original reaction. I'm going to make sure that the atom, if it's sulfur, that's being oxidized or reduced is, if there's a subscript in it, I need to make sure I have the same number on each side. So if I started with 2 sulfurs on the left, I have to have 2 on the right, even if it's just making S on the right-hand side. So I would adjust that. I can't change the subscripts, I can only put coefficients in front with the one that has less. Then, if it says it's happening in an acid or base solution, I may need to add oxygen for any missing oxygens I will balance in the form of water. So I'll add water to the side that has less oxygens until it has the right number of oxygens. And I'm only going to do this step if it says it's happening in acidic reaction or in a basic reaction. Same thing, after I've added water to balance out the oxygens, I also added hydrogens. So then I'm going to balance that out on the other side by adding H+ ions to make sure that the number of hydrogens are balanced. And then after that, if it's in base, I will also add the same number of hydroxide ions to each side to convert any into water. I'm not going to do, we might do one base one. But I've asked you some acidic ones on the homework. By the way, fun fact, I won't ask you to balance in acid or base on the test, just on the homework. So you will have to do the rest of this, but the step 3 and step 4 I won't make you do on a test. And then finally I add in the electrons. So now I use the oxidation numbers and how many of them atoms there are to determine how many electrons are needed, and I put them on the appropriate side. So I'm going to put them on, the electrons are always going to go on the side with the let's see, it always goes on the side with the more positive. Yeah, the more positive oxidation number. So I add them to that half reaction. Once I've done all that, I now have 2 balanced half reactions. At this point, I'm going to determine the scaling number. If I have 2 electrons in one and 4 in another, I will multiply the one with 2 electrons by 2 to make sure they both have 4 electrons. And I'll just, if I multiply by 2, I multiply everything in there by 2. Then I will rewrite those, and then I'm going to add all the half reactions together, and when I'm done I can remove the electrons out. Okay, so let's balance one. All right, so I'm given carbon plus Fe2O solid makes CO2 gas plus FeS. I give you that reaction. If it didn't say anything about in acid or in base, which was frequent, we're going to now work on assigning the oxidation numbers. Note that I didn't assign the oxygens because it's oxygen within a compound, I can assume it's -2. Oxygen within a compound, I assume it's -2. So since it's not changing, I didn't show it. Here, carbon is 0 because it's an element. Elements are 0. Over here, iron is 0 because it's an element. Elements are 0. But this is in a compound. I'm going to need to do some math and figure out if oxygen is -2, that means this one is in the +3 state. Remember, iron is one of those type 2 cations. It might be 2 or it might be 3, so double check the math. This one's +3. Here, I know that if oxygen is -2, and there's 2 of them, that's a total of -4, carbon has to be a +4. So I've determined the oxidation numbers and I didn't even have to draw Lewis structures. So it looks like carbon is going from 0 to +4, so that's increasing, that's an oxidation. Iron is going from 3 to 0, it's reducing, so that's a reduction. So now I'm going to break it up, I'm going to write the oxidation half reaction first. So carbon is on the left, CO2 is on the right, and now I have to figure out, well, how many electrons does that take? So this is +4, this is 0, that's a difference of 4, and it always goes on the more positive side, so I'll put 4 electrons there. Then I'm going to do the reduction half reaction. So I start with Fe2O3 is on the left, Fe is on the right. Since there's 2 irons, I need to have 2 Fe, so I'd have to add in that 2 because I couldn't have started with 2 irons but end up with just 1. And when I do that, I recognize that each one needs 3 electrons, but there's 2 of them, so it's a total of 6 electrons. So now I have a 4 and a 6. I have 2 balanced half reactions. And again, I didn't have to do that adding waters and hydrogen plus because it didn't say anything about acid and base. So now I want to make sure both of these have the same number of electrons. So I'm looking 4 and 6, they're not the same. I'm looking for a number that both 4 and 6 go into. The smallest number is 12, so I'm going to get to 12 for each of these. I'm going to multiply this one with 4 by 3. So it's going to be 3 CO2, 3 C's makes 3 CO2 plus 12 electrons. And I'm going to multiply the second one by 2 because 6 times 2 is 12. So 2 iron oxides plus 12 electrons makes 4 irons. So now I have my 2 electrons, 2 half reactions. They have the same number of electrons in them. I can add them together. I know that the electrons are going to cancel out. So I can first write the whole thing. All the reactants stay on the left side of the arrow. All the products stay on the right side of the arrow. So 3C plus 2 Fe2O3 plus 12 electrons arrow. 3 CO2 plus 12 electrons plus 4 Fe. And then I can cancel out the electrons because there's 12 and 12 and remove them. And I'm left with 3 carbons, 2 iron, 3 oxides makes 3 CO2, 4 irons. Here's another example. I'm just going to step through it kind of quickly. If we assign the oxidation numbers, aluminum is going from 0 to +3. Hydrogen is going from +1 in the compound to, it's an element, so it's 0. These aren't lined up, but so our oxidation is the one 0 to 3. That's aluminum going to aluminum chloride. That would take, there's only 1 aluminum, that would take 3 electrons. Goes on the more positive side. The reduction half reaction, I have H is +1 going to H2. Since there's 2 on the right side, I need 2 on the left side, so I'll start with 2 HCl. Each one required 1 electron, so a total of 2 electrons. 3 and 2 go into 6, so I'm going to multiply the first one by 2 and the second one by 3. And when I do, they're both now 6 electrons. I can add them all together. 2Al, 6HCl, 6E, arrow, 2AlCO3, 6E, 3 hydrogen, and then I just rewrite it without those electrons.